Okay, welcome to today's lecture. It's an important milestone of your senior design project. So explaining in 4 minutes what you are doing to people who may not necessarily know too much about it. So it's a challenge, but that's part of the exercise. So we have a busy schedule. We want to be out here before 6 because there's going to be food delivered at that time. But we have a couple of announcements to make. So I think, Brianna, you want to say a few words about HKN, very important, and then we'll give you some announcements. And Sid always wants to say something, so he will talk at the end. Yeah.
Okay, hi. So you may have seen some posts on this already, but every year Eta Kappa Nu sponsors a freshman mentorship program for senior design. So that's where you can sign your teams up to host a freshman, where a freshman will work on your project with you. This is good if you need an extra set of hands, or if you are interested in like mentoring freshmen and showing them what it's like to work on hands-on projects. So it's been successful in the past, and we rely on you guys to sign up. So you can sign up at this link here, and we'll match freshmen, and you get a choice in which freshman you get.
It's also on the Piazza.
Yeah, it's on Piazza as well.
All right. In terms of upcoming important dates, executive summaries due on December 3rd. Your posters must be emailed to ESE Senior Design at SEAS by December 6th at noon, and December 7th is the demo day. Next week, DETCON's going to be pretty busy with ESE 111 stuff, so it's probably best to try to get most of your work, if you're working in DETCON, done this weekend, or do it in senior design. The TAs are going to be holding their office hours in senior design to make it easier for you.
Okay.
Yeah.
You will, when you come, please speak into the microphone. There are two. If you want to use the clicker, that is the clicker. If you want to feel good about using it, many people want to stay on the keyboard and press the keys, but we have two cameras rolling, one right here, one from the top. We weren't sure one from the top was working or not. That's why we have a microphone. So please, when you speak into the microphone. Watching you from the back. If he can't read the slide, he's going to make a comment about it. Okay? But that's why it's in the back. Let's keep it prompt. You know your team numbers. Try to be ready as soon as one team finishes. We have uploaded all the files onto the local drive that you'll be able to see, so you don't have to worry about transition. And no Q&A. All your comments go on that piece of paper. Please make sure you write your name behind that piece of paper. We won't reveal it, but we just want to know if you the good questions before we go nonstop. Yes. Okay, in the back. Anybody else? Everybody got piece of paper? Everything good? Are you need? All right, teammate. You want to say something?
No.
Wait, how do you? What's it?
Oh, unmute.
Okay.
All right, team.
There's 2 microphones.
No, I don't think we need one. Okay. Where do I point it out? Okay.
Just so that you know, ESE 111 students might come in and put pressure on you guys. Yeah,
Ready? All right, good afternoon, everyone. We are Team 8, and we are working on a PIV infiltration detection device. So taking a look at our fall semester, just to summarize, we were able to meet all of our fall milestones, and currently we're working on our first prototype. This device has a heavy emphasis on minimizing nurse workflow. We were able to kind of study this through an in-depth analysis of human factors. So moving forward, looking at our spring semester, we're going to continue testing our device, trying out different sensors to find the best one From there, we'll begin testing on pig livers before we test on actual patients. This device will also include a modeling component factor for a remote app, as well as a visual aid component so that it can be used in the hospital. And in addition, we'll continue to have our bi-weekly meetings with our subject matter experts and our advisor.
All right, a brief recap of our problem that we're trying to solve is PIV infiltrations, primarily in children, as the usual method of detection is manually due to nurses, and this method, when it goes undetected, can lead to bruising, scarring, nerve damage, etc. So we're trying to create a device that's going to detect this early on, while also minimally interrupting the workflow of nurses. And so some of the considerations we have for this device are creating something that's minimally invasive to the patient, something that's capturing real-time data with 2 different sensors, as well as something that has easy to interpret results for the nurses that are using them.
So given this design criteria, our device will take in biological inputs from the patients that are associated with the symptoms of infiltrations. And in our case, we're focusing on temperature changes and swelling that comes with infiltrations. And so the sensors then that we use to detect this are a strain gauge and thermal sensor. And the sensors will wirelessly transmit this data into a remote application that'll run a detection algorithm using MATLAB or Python and filtering techniques, and then display the results on a dashboard and alert the nurses if necessary.
So to meet the requirements for our design, we're implementing a hardware and software solution. So this semester, our hardware consists of using 2 kinds of strain gauges, a rosette and a linear strain gauge with different degrees of freedom, and a thermal sensor. Those will be connected to an Arduino and implemented onto the patient via Tegaderm, which is what the nurses currently use in their workflow. And in terms of software, we're transmitting data from a Raspberry Pi to a remote computer and using Python for analysis. In the spring, we hope to take the data we have from the sensors and filter that with hardware and software, and then implement a flexible circuit board into the Tegaderm. And for software, we're going to build out a structure to fit the model. In terms of our budget, it all comes from the hardware, where we're using a combination of sensors, flexible circuit board, Raspberry Pi, and the Tegaderm for the patient.
So for the stakeholders we're considering the patients and staff at CHOP and HUP, specifically the nurses that would be using this device. And then for some of the engineering standards we'll need to consider, so since we want to test on patients, we're going to need to get IRB approval. We'll also need to comply with HIPAA. And then in order to get this device implemented into hospitals, we'll also need to get FDA approval. And then for our implementation and testing plan, our current bottleneck is determining the type of sensors and looking at critical frequencies and temperatures that we'll need to detect the infiltrations. And then we also will need to work on combining the different aspects of our project, so the software components, the hardware components, and our human factor analyses. Then for a timeline of this, so first we'll be testing in pig livers to get proof of concept, then do patient testing to calibrate the sensors and get patient feedback, and finally we'll be focusing on our target market of the NICU and the specific human factors analyses here. So thank you.
All right, piece 13. Try to stay in the center of the stage, please.
All right, hello everyone. No, she said we. So we are Team 13. We are NeuroPoint, and today we're going to be talking about what we've accomplished so far this fall. So just looking at our timeline here, you'll note that we have accomplished some of the tasks that we've identified for the fall, most of those being associated with our 3D printer. So we have got that assembled, and we are able to control that via a computer using G-code commands. We're having a bit of a problem with our profiling tasks just because we've had a component on the printer that isn't working as it is expected to work, but we are working on debugging that now, which should hopefully, get all figured out by demo day next week. And then looking forward to the spring, there's a couple of other tasks that we've identified here, mostly interfacing with various resources that are already online, like the Mouse Atlas, which has a whole bunch of data regarding scans that have been done on mice's brains. And then lastly, we're going to want to create a working GUI so that a user is able to accurately use the system and, of course, perform testing.
Okay, and then I'll just talk about reminding you the what and the why of what we're doing. The problem that we're trying to solve is that current neuroscience research that operates on the brains of mice is extremely difficult because it's a very small target, it's prone to a lot of error, and there's really not a good way to know what you're doing until after you've already done it. So we're trying to automate that by scanning a mouse's skull and then using that scanning information to figure out what orientation the mouse's brain is in. So it can be operated on also by the same machine. And here's our block diagram of simplified of what our current design is. We have a Raspberry Pi hooked up to a LCD screen, which you can use a mouse and keyboard. Maybe we will look into a touchscreen capability at some point to input commands, which goes to a Python script on the Raspberry Pi that calculates, using the Mouse Atlas, what the coordinates of your target within the, thank you, can calculate using this Mouse Atlas, which is like a map of the brain, what you're aiming for. And then it interfaces with the 3D printer, which has built-in motors and a translation stage and can move the surgical tool or scanning device where it needs to go. Currently, we're doing this using software called Pronterface, which is a way to write scripts in G-code, which send like movement commands to the 3D printer. We would like to ideally be able to do that directly from a Python script, which is something that we may work on later in the semester or at the beginning of next semester.
So in terms of the technology we're using, in the case of hardware, we're using the Tron XY X5S 3D printer. As Chris mentioned, we are using the mechanical design of a 3D printer to turn it into a scanner, which will be used to scan the mouse's brain and create an atlas from it. We're using a linear potentiometer for profiling, and we're also using a Raspberry Pi. The prices are listed over there. In terms of software, we're using Marlin, which is the 3D printer operating system. We're using an application called Cura, which we use to send single commands to the 3D printer. That's how we are interacting with it. And we're using also Pronterface, which is an application that sends full scripts of G-code to the printer. Our plans for the spring are basically to obtain and integrate a higher precision profilometer and to develop a GUI to be used to control the surgical device. So now this is a video of what we can do with the printer as of now. So this is us manually sending commands to the printer to move the nozzle. Then using Cura, we can send single commands, and the printer does it. And using Pronterface, we can send a script of commands that the printer follows.
And so basically to wrap up, where we are now, we have 3D control of our printer, so we can say make a move in X, make a move in Y, make a move in Z, or do any linear combination of that. So we feel like we're getting really close to the profiling technique, and hopefully by demo day we'll have something to show for that. And in the end of the day, like we said before, we're working towards a laboratory application for researchers. So that's been our main concern, and we'll keep looking at that as we move forward with our standards and as we work towards more and more precision. So thank you very much.
Hi, so we're Team 20, we're PennGo. So looking at our milestone chart, the ones that are highlighted in green are the milestones that we have met. So as you can see, we've met most of our milestones. A lot of the background research going on Penn buses, surveying students, and we've already started working on our algorithm and mock-ups for our app. What's highlighted in yellow, I'll talk about in a minute, that's stuff that we decided to change. So in terms of our milestone achievements, we've met most of our milestones, but one of the reasons we think so comes from a lot of demo day feedback that we got from MVP demo day, which is that our timeline was very conservative. And so for the spring semester, we're really looking to push it forward in terms of getting our app development done by January. By March. In January, we're going to start collecting feedback. And when I talked about that we had changed some of our milestones, we originally were going to do a census tract matrix, which would model demand in the Penn community. But unfortunately, we realized the Penn community is very small, and it was very hard to model demand, which is why we changed to a feedback system, which Gabe will talk about. And then last thing for spring semester, by April, we want to get our first route suggestion to Penn Transit so we can work with them on implementation.
So the problem we're dealing with is that Penn students don't really use Penn transit systems, whether it's due to a lack of awareness or just inconsistencies in the system. So we're building an app where the user would input their desired destination and the output would be the optimal route to take to get there, as well as a feedback system where users can actually request new routes or changes to already existing routes. And like Julia said, we're not going with the census tract matrix because we feel that user feedback gives us a better idea of the true demand in the community.
So there are two main components to our project. The first one is the mobile app. So our algorithm is going to take in the user inputs along with the Google Maps API, the live tracking API, and then the bus schedules, and it's going to output all the routes for the different bus routes and then rank them based on which one is the best options for the riders, and then that will be given to the user of the app and they can choose the best one. And then the second part is the feedback one. They're going to pick a route, a time of day, and then there's going to be a weight to it, which is the number of votes it gets from the other users of the apps. And it's going to take those existing routes and those suggestions, cluster those suggestions so the ones that have similar locations are grouped together, and then output either an adjusted route time, an adjusted route, or an adjusted stop, and then we'll give that information all to Penn Transit.
Yeah, so our technology is mainly software-based, and for the mobile app, we'll be likely using React Native, and we'll be incorporating things like SEPTA source code, the Google App API, and live tracking data like Jordan spoke about. And then in terms of network optimization, we're likely using Python, but we're still working with our advisor to figure out if that's the best tool for us. So for budget, that will include the $100 Apple developer's license and potentially a network optimization tool if we don't go with Python. And Julia will show you a little video of our design mock-up. So this is the map route ranking algorithm. You can get directions. We chose Penn Bus West, and it tells you timing, how to get there, all the other options. And then the smiley face is our voting and recommending routes. So there you would input your suggestions and then also vote on other people's suggestions. And then as far as implementation, our stakeholders are Penn Transit, Penn students, Penn faculty, potentially Drexel if they decide to work with us, and SEPTA. And then testing, we want to test our design to make sure it's user-friendly. We want to test the accuracy of our rate ranking algorithm to make sure it's outputting the best routes. And then we also want to test the feasibility of the recommendations that come out of our feedback system. And then as far as engineering standards, there's user data privacy considerations that we have, but since we're collecting the data in aggregate, we don't think that's going to be an issue because we're also not maintaining the data. And that's it. Thank you.
Hi guys, we're Team 9, we're Respiradar. My name's Danielle.
I'm Blanca.
So this semester we've been working to solve a problem with respiration detection. Just a reminder of like what we're doing. So traditional methods for respiration detection in hospitals or outpatient care usually includes bulky equipment that can often interfere with sleep quality, which kind of defeats the purpose of the monitoring system. So our solution involves an ultra-wideband radar front-end hardware system, which feeds data to a software backend for real-time analysis of respiration detection.
So these are our fall 2018 milestones. The main purpose of these was to gain a proof of concept for the whole system. On the hardware end, that involved building a fully connectorized system to sort of understand subsystem integration. And for the software end, we had to use custom-built Gaussian monopulses and time delays to sort of build out the algorithm for distance measurement to target. Had to do this until the hardware team is completely finished and can get real-time data to use.
So as Will said, once we worked in this fall semester to have sort of a proof of concept with the connectorized version, our next plan will be in the spring semester. We want to fully integrate this system, which we plan on doing by designing the circuit onto a printed circuit board. So for the hardware side, that will consist of actually designing and then testing this printed circuit board in late January, early February. And then on the software side, just working to continue that algorithm so that we're turning that distance that we're measuring into the respiration rate, which will like tell us that. And then fully integrating this system, so taking the hardware and software and making sure that we can accurately measure the person's respiration rate, which we plan on having done by mid-March, late April.
Yeah, so here's a video, maybe. Yes. All right. Skip the video. Going on to the video is just showing basically hardware testing. So what we've done with that so far is characterized all the connectorized components and then done range measurements using test equipment. So basically send the pulse from a pulse generator on one antenna, then that antenna goes across the air through our channel into the other antenna, and that's received through our receiving hardware, amplifier and which is an amplifier and filter, goes to a sampling oscilloscope, which displays the pulse on the screen. As we move the antenna, we can see the pulse zero crossing move in time, which is eventually what's going to be translated to the distance to get respiration rate. So talking a bit about budget, most of the budget in the fall has been this hardware connectorized version. We spent around $300, and that has involved the receiver hardware, so the low noise amplifier and the filters associated with that. And moving forward to the spring, we estimate a budget of a few $1,000s, most of which would be components, though if we get those samples, that's free, but the PCBs as well are pretty expensive, and we hope to do 2 iterations to improve upon mistakes and performance issues on the first iteration. And then to talk about standards and testing, as Blanca mentioned, we hope in mid-March to begin finalize the design so we can actually do testing on real targets. And if that goes well, we may consult with medical professionals about how the testing would proceed in a hospital setting or an outpatient setting, which could be a potential use. Right now, though, most of the testing is going on in the lab where we have the RF test equipment we need, so characterizing all the circuits and then seeing the signal go through the air, checking the algorithm, how it performs in a noisy environment,
And standards are a big thing in terms of the hardware. It constrains us on our output power. The FCC standard for the ultra-wideband frequency area we're working in is negative 41 dB, so that kind of constrains our gain for our transmit setup, and that also has constraints when it comes to the receiver because we have to make sure our sensitivity is high enough to meet the range requirement we want. Thank you guys for your time, and we're excited to demo to you guys next week.
Should I just keep trying? Should I send it again? Maybe skip us and then we'll go.
You sent it to me.
What's your name? Oh, right.
By the way, there's a timer.
Sweet.
Hi everyone, we are Team 17 and we're here to tell you a little bit about how stakeholder democracy is doing. So far we've been able to meet a good amount of our goals. We had some new information come in with our MVP demo, or more like a new development, where we realized that our platform needs to be able to accommodate cities with multiple levels of government hierarchy. So we're actually kind of going back to the drawing board a bit and trying to integrate like city government structure into our platform. And so that's kind of extended the timeline on the back end of the platform a bit, but otherwise, platform's going strong. We have a UI and everything.
Yeah, to help guide our development and testing, we developed a few different flowcharts that basically they really helped us a lot, and they will help us with, especially with constructing the database and with the design of the system as well, and the multiple levels of processes that we have. And this is a demo of the platform that we have. We have it now. It's much improved visually and in terms of functionality than the last iteration that we had. And basically, this is normally animated, but it just displays that you can vote on certain. You can create polls. You can vote. We have it styled with Bootstrap, and we're looking forward to adding a lot more to this to. More functionality.
Yeah, so I'm just going to talk a little bit about the technology we're using. So for the backend, we'll be using Python because we hope to like be able to do more data analysis for stuff like comments, to be able to like do like text analysis so that government administrators can be able to know like what are the trending issues that people are talking about, like, and some of the keywords. And so for just the UI and just basic like connectivity, we'll be using PHP and FastCGI. Which is supported by the Apache server. And then lastly, like for now, for testing, like we'll be using Google Cloud to store our data and just for development. But because this app is going to be eventually outsourced to like government, different government agencies, they'll be in charge of their own like server storage and associated costs. And then now, just speaking about Berger, we anticipate that we might use up to $300 because as we test a project next semester with actual focus groups, providing stuff like snacks and just like menus and stuff like that, that is our main thing, because since everything else is dependent on just the software, that's essentially free, and like for stuff like Google Cloud, you can use like student accounts and get discounts and stuff like that. Yeah.
Yeah, so for standards, we're currently meeting US Open Data standards, since we're using software that's licensed under FSF and OSI. And as well, we're also meeting City of Boston and City of Philadelphia's digital design standards for official websites. We're also aiming in the later versions of the platform to meet full ADA compliance and accessibility standards. Yeah. So right now our 3 options for testing are working with a Philadelphia City Council, most likely in the Northeast, or a local organization like a Rotary Club, or finally a Penn organization or dorm. And the key areas that we need feedback from our stakeholders are further functionality of the platform, level of engagement and area of interests of the stakeholders, and overall efficiency of the platform on the user end, as well as the government side. So thank you for listening.
Are we going to go team 1?
Team 1.
Hi everyone, we're Team Group 1. We are building a smart stethoscope, and the problem that we are primarily tackling is the reality that a cardiologist can't be with a patient or with a human 24/7. But it would be useful, especially for patients who are prone to heart murmurs or arrhythmias, which is a condition that typically arises during strenuous physical exercise. So what we've decided to build is a stethoscope device that is continually listening to your heart, something that you wear 24/7, and it's analyzing what it's listening to, the amplified heartbeat sound signal, in order for it to then perform a learning model on top of and analyze whether or not you're prone to any problems for which you might seek the doctor for. Originally, at the start of the semester, what we planned on doing was creating an MVP version of the hardware version, which is a simple electronic device, which we can then pick up a heartbeat sound with. And then the software version, which is a classified heartbeat sound labeled data set that we found from Kaggle. We were able to accomplish both of these goals this semester. And the third thing that we were trying to also think about was also implementing a blood flow sensor, which under the direction of our advisor, Jim Weiser, he actually recommended that we maybe push that off after we've integrated the hardware and software together in order to make sure that we can actually get the project working. So with that, Jared's now going to talk a bit about the systems architecture.
Thank you, Jonathan. So our system consists of a hardware component and a software component. The software component on top, we have an external data set from which we can create which we are creating a machine learning model. We're creating a training model and then using that to train the output. On the bottom, we see more of the hardware. That's like audio processing. We record the actual heartbeat from the human, amplify the signal, pass it to the software machine learning model so that we can predict 2 things. One is the classified output, which is used for the patient to figure out if they should see a nurse for like an initial diagnosis. And second, a log of the audio signals that are amplified so that it's good data to show to the actual nurse so that they can provide further feedback. Then going into the hardware, we have some audio forms waveforms that we've been working on. On top, you can see this is a regular recording of a heartbeat. And on the bottom is after we pass this recording through our device, which consists of the microphone and the amplification and some basic signals processing, we wind up with the second audio waveform on the bottom. And this shows that our system, it's a good proof of concept that we can take an audio signal and we can capture enough of it in order to pass it to the machine learning algorithm and make accurate predictions. Now I'm going to pass it to Jason to talk about the software.
Yeah, so on the machine learning side, we're taking labeled data from the internet and using it to train a convolutional neural network. And using these deep learning techniques, we can take audio recordings, whether they're from the internet or captured by our device, and classify them into normal, murmurs, or just other sound artifact categories. And you'll see on the diagram, on the red line is the accuracy, so we're able to get pretty high training accuracy right now, and we're looking forward to continuing to improve the model.
Yeah, so in terms of actually capturing the signal itself, which is an important part of the project, obviously, we have the first version, which is a digital MEMS microphone built into a stethoscope, and that's actually where we got that signal you see there. The problem with that is it's really meant for like speaking and picking up other noises. So we're currently building a second version, which uses a piezo resistor, which is what they use in electric guitars to pick up the sounds. That's an analog signal chain, so we're in the middle of moving over like the signal chain to be analog, but we do have good proven data from the digital, so we can kind of dual path the rest of the development. And then in terms of the testing, the stakeholders and everything, we're looking at college students who do have heart murmur issues, who are like moderately athletic and want to engage in activities, but will eventually open it up to other heart diseases we can find that have labeled training data sets. We're trying to build the actual device you can wear as quickly as possible so that we can implement our testing. Right now, it just involves doing some push-ups so we can get the sound a little bit louder, but we are building an amplifier so we won't have to do that. And then finally, in terms of standards, just FDA medical device standards, but because it's a class 1 device with an exemption, just as long as we don't, tell people, stop using your medication, doesn't need to be notified or anything. That's it. Thank you very much.
Guys, while they are getting ready, let's give a big round of applause to our wonderful TAs, Saitya, Will, JJ, and Julia.
Testing.
All right, hey guys, we're Team 16. I'm Rabil.
Abdul.
I'm Doug.
Joe. And we're working with Victor Preciado. So, so the problem with current predictive algorithms or neural networks is that they're unable to generalize over new input data, and that they predict the future through averaging. And we're working with something new called GANs.
So here's a look at a generative adversarial network. It consists of two neural networks, the discriminator and the generator. The generator is given random noise, which then tries to output something that resembles the real data that it represents. And then on the discriminator is given the real data, and the discriminator then determines how real the data that it's getting, and it goes back and updates the weights in the discriminator and the generator networks. And you do this over and over again, and then you have neural networks that are better equipped to predict data of chaotic systems than the traditional ways.
All right, so what we wanted to do was build, again, or a generative adversarial network on time series data.
when you do this, or time series data can be very important, and especially like, let's say you're working with private hospital data of patients, but you don't want to release this information. Instead you can do is generate synthetic data of these patients, with also time series, and then you can release this to the public. So it's important to be able to build something that can generate good synthetic data on time series, but instead we decided to work with the stock market for now, just building again on the stock market, initially see what results we can get. So when we train the generator and discriminator, these are kind of the results you get. These are typical, and just you get like an equilibrium eventually. We train it for 50,000 epochs, which just means iterations. The way we did this was we decided to look at the past 20 days. So we would predict on the past 20 days, and we'd predict ahead on this case for 5 days. And this is just for 0% change. So we just want to see if there's any up or down movements, if we can predict anything 5 days ahead. We see that for the generator, or the GAN network, so this is a confusion matrix. So you want the diagonal to be dark. It predicts most of the down and the up movements correctly. But it turns out that just being able to predict if it's going to go up and down within like the next 5 days, it's not really very helpful. So we want to predict like some percentage change. It can go up or down in 5 or 10%. In this case, it's interesting that the GAN, or the generator the GAN is only able to predict the downs correctly. The ups, it's completely wrong. It's about 1% of the ups it predicts correctly. We decided let's make it a bit less, like 1%. Let's check 1% out. It's a bit better. Here we're at 14% correct predictions for the up movements, but there's still a lot of work to be done. And for our milestones, we hit most of them. The only one that was, I guess, suspect was for November 6th. We were supposed to train on all the data sets, or all the stock companies, but we didn't do that. We only worked with one. And that actually reminds me of another point. So for currently, we trained this on 30. We looked at the market cap and picked the top 30, but that didn't really work out. It didn't give us good predictions. So we had to go with S&P 500. But there's a lot of different ways we could approach this. We could pick a different subset of companies that could maybe give better predictions. We could change the layers that we're using, the depth of the layers. We can change the parameters, the indicators that we're currently using. And yeah, there's a lot of work to be done.
And for the technology, as we phrase this as more of a data science project, so we primarily use Python, its related packages on TensorFlow as well as Jupyter. And for the data budget, it's actually zero because we get all the open source softwares as well as from Alpha Vantage to get all the data points. And more on the additional information, stakeholders, everyone who's interested in forecasting with chaotic systems, and implementation, realization of GANs using TensorFlow, as well as verification using statistics. And more testing need to be done through measuring GANs against benchmark, such as CNN, RN, and also tweaking the parameter as well as adjusting data inputs. And the standards, since it's all based on public data and we have no intention of commercialization, so we have no applicable engineering standards right here. So thank you very much.
Thank you.
Good afternoon. So we are Team 19, also known as PODs. So to start off as milestones, among the many that we had, these are kind of like the top three for the fall. So our first one was just kind of create a playable game. So for any of you that remember, we created a simple game of hide and seek. So that was the main milestone that we wanted to accomplish in the fall. And then we got some data collection. It's in the basic stages right now, but we were able to collect data from people playing the game. And then our last is to host a game online that we'll eventually achieve come demo day next week. And then for the spring, we want to create additional games along with hide and seek, improve our data collection so that our researchers can actually utilize the data, and then eventually develop a framework that will allow for the creation of more and more games.
So just kind of recap what we're trying to do here, like a little more context for the games we're doing. These like strategic situations kind of happen every day, from like simple things like a game of rock, paper, scissors to like making travel plans to like larger scale things like governments organizing evacuations. So there's a lot to be gained from studying them, but since people don't behave rationally or predictably, it's kind of, they're pretty hard to model. So what our platform, what we're trying to get set up is a way for researchers to be able to easily collect data for just a number of different situations from real people to then apply to their questions.
So as far as our design, our main back end is where all the decision logic takes place. This is kind of the backbone of the whole platform. And users will interact with this through a website. They'll play the games, and their decisions will be sent to the back end, and it'll do all the processing and figure out the results from what the users decided. At the end of the game, these decisions are sent back through the website to show the users their immediate results, how they performed. But these are also recorded in our data processing, where we keep track of the all-time performance of certain strategies in different games, so we can keep track of which are the optimal strategies. And the users who created these games can go back in and see what the total results were and what the optimal strategies were. The technologies we're using for this are mainly JavaScript, making client and server interactions through Node and Express. We plan to host this on Wharton's AWS servers. Our advisor, Stephen Kimbrough in the Word department, he said he could give us 6 months for free on their servers. So in the future, maybe we'll have to splash out a bit, but I don't think that we'll accumulate too many server costs there. For the data reporting, we're using Plotly for all our visualizations.
So for implementation and testing, our stakeholders will be researchers, either at academic institutions or, like commercial companies, like market research kind of things. The participants on the other end be students or focus groups or employees. And then our testing goal, we want to be able to have this ready to use in Professor Kimbrough's OID class next spring, or this spring. We wanted to be able to have it to support his whole class using it at the same time, and then have the data ready for him to use. The standards we're having to be complying with be the IRB standards for human research, and then there aren't too many privacy concerns here in the US, but should we expand, we might have to consider GDPR. In addition to accessibility standards for visually impaired people.
All right, so we're Team 11, and our product is the Bilateral Limb Assessment Technology, or BLAST. And so the problem that our team has decided to tackle is the fact that clinicians currently don't have an objective way of assessing children that suffer from neurological deficits, such as cerebral palsy. And so these different deficits make it hard for them to complete what's known as ADLs, or activity of daily living. This includes like brushing your teeth, brushing your hair, or even putting on clothes. And so the way that the clinicians currently assess the treatment progress of these patients is through a subjective means based on visual cues. And so what we hope to do is by providing these these measurement devices coupled with metrics that we can help the clinicians objectify this process while being able to provide more unique solutions for the patients.
So our current solution consists of two components. We're using Python to control a Connect to gather skeletal tracking data. For hardware, we're using an IMU to track rotational motion, as well as a flex sensor to track finger bending. These two are being integrated with a LilyPad, which is a compact microcontroller that can be sewn on the back of a glove. And the software and the hardware will come together in a GUI for data analysis that will be presented to the clinician in a readable manner. So we're trying to keep our solution low cost so that it can be implemented widespread at hospitals and clinics. So our current budget for the semester is about $66.
So over the course of the semester, our milestones have shifted, in particular in the software component side of things, where we transitioned from open pose to connect for pose estimation. And one of the main reasons we did that was to minimize processing time and get real-time feedback. And then looking onto the hardware side of things, we were able to successfully implement the IMU and flex sensor on the glove and get pretty accurate data. And then looking forward, we're hoping to work out some of the kinks in that integration for next demo day and look more into the analytics of Connect. And then looking more forward into the spring, we're hoping on building up the data analysis and metrics and GUI just to have a better user interface so the physician can clearly read the data and doesn't have to do any other analysis aside from just opening it up. And with that also goes making our solution wireless. So from that, we'll transition into preclinical assessments where we will refine our ADLs and metrics.
All right. So this is just a video to show that the components of our device actually works. So we're able to get skeletal tracking as well as joint positioning in the XYZ direction with Connect, and you can see that it's pretty accurate. And so the next step is just to show that the IMU and the flex sensors were able to work in terms of like being able to collect the data and seeing the accuracy of that data. So if I skip right here, so you can see that the values change as she moves the gloves over, and like by next semester, by the end of this semester, maybe we can like integrate both the software and the hardware components just to make sure like everything works properly. And in terms of testing, by next semester, mid-February, we hope to have preclinical assessment, as Alpha mentioned early on, and that just means that we'll be working with our stakeholders, occupational therapists at HUB or CHUB, as well as patients, and just to test that the device actually works and it's user-friendly. And in terms of standards, we're able to complete the HIPAA compliance as well as city training, and the next step, or the last step, would be getting FDA approval, and we're on the class 1, meaning that our device creates minimum harm to the patient and is actually beneficial. And that's it.
Hi, are we starting? Sorry. We're FunRight, we're Team 7. Brayden, Alec, Ralph, and myself, Christina. We're working with Professor Peter Fader. How do we move it? Okay, so first of all, our milestones, we're pretty on track, which is good. We've fit a couple of models. Well, we started off the semester by exploring different models that we could use, collecting the data, cleaning the data, testing a couple of models, and then we're going to focus next semester on adding more variables to the model, testing out different covariates, and then hopefully testing our model in a real-life situation, and then doing the interface for it. So, yeah.
So I think we realized that a lot of you have been struggling to understand what our senior design project is about. And partially that's because there's a lot of financial engineering involved. So we decided that we just wanted to briefly recap what it is that we're doing. So currently the situation is that right now, if a random organization needs financing, they go to a bank and they request a loan. However, that's very hard for nonprofits because nonprofits don't have a predictable source of income which they can use as a covenant to guarantee that the bank will, to guarantee the bank that they will repay them. And therefore, there's this need in the market for financing for nonprofits. What we're trying to do is this thing called factoring. Factoring means that a specific organization will quote unquote lend money to a nonprofit. However, they do not expect the nonprofit to repay them. So essentially, it's a transfer of risk. What this means is that the organization will give financing to the nonprofit, and in return, they will ask the nonprofit to capture the donations that are going to them for a specific period of time. What we're trying to do is build a model that gives us two outputs. The first being how much can an organization lend to a specific nonprofit, and the second variable or the second output would be what is the period of time in which that the organization requires in order to collect their donation and hopefully make certain profits.
Sure. So we're working with a company that's operating in the market today that has access to these donation behaviors. Fundamentally, what they do is they have a series of tables that we've been able to have access to, specifically their transactions or their donation tables. We're using these donation tables as inputs to several stochastic models. And then with these models, we're using it to build projections over the next month. Cynthia, if you can click the demo link. Wherever it is. What just happened? It's going to work. Maybe. Theoretically. All right, that just didn't work. Effectively, we've been able to do this. So we've just we ran a test, an out-of-sample fit test over the last month, and we're successfully able to both predict their cash flows as well as, in theory, offer financing behind those cash flows. So there it goes. So what you're seeing is the orange line is our predictions. The green line is what actually, or the blue line, the line that's moving is what actually happened, and the line at the top is break even. So in this scenario, we would have given $12,000 to this nonprofit organization, and over the course of the month, they will successfully pay it back. The ROI on this loan was about 4.6%.
There's one here. Okay, all right. Okay, yeah, so we're kind of running out of time here. If you want to go to the next slide, I'll talk about the models that we have. So in our software so far, basically, the model that we've used that's worked really well is a negative binomial distribution that takes into account primarily history and frequency. We tried to use a Pareto MBD, which also adds the recency of transactions. And the way that our data is structured, we realized that really didn't work. So if you look at the graphs here, the NBD, our actual versus expected, is really, really close. For the Pareto, it's like completely out of whack. And then you want to go to the last slide. In terms of stakeholders, the primary stakeholders are Flourish, which is the organization that's giving us all of this user transaction and donation data, and then the nonprofits that we would theoretically be giving money to. And our goal is to start testing our product next semester.
All right, hey everybody. We're Team 3, My Meme. We are the Tinder for Memes group. We have Anish here. I'm Devin, Saku, and Darius. So I'm going to dive a little bit into our milestones real quick. We have a lot up there, as you can see, but basically what we've been working on is designing the clustering algorithm for the memes that we currently have. We spent a lot of time determining what attributes we exactly want to use for our memes. So we've actually had to push off designing the suggestion algorithm, which will basically suggest users memes based off of memes that they've liked and disliked in the past. But by demo day, we basically hope to have a working example where you can basically like or dislike on memes, and then it will suggest you memes. In the spring, we hope to basically refine these, maybe pick better attributes, and hopefully design a web iPhone or a web application. So moving into our problems and solutions, as many of you meme consumers understand, there's a lot of content out there, a lot of platforms, whether it be like Facebook or Twitter and such. And then what we hope to give is enjoyment, and we hope that people will hopefully become more popular when they share their memes with their friends, and have more entertainment. So I'm going to pass it off to Anish.
All right, thanks, Evan. So at the heart of this is a recommendation system based on what we define as attributes for the user and the meme. These are the same. We spent the last few months iterating over these attributes. We have a list of about 12 attributes now that we kind of settled on. Now, it works by starting a untrained user and then giving a predefined set of meme to them with where they will swipe yes or no on the memes, and then you will train the user attributes based on that. And then long term, once these user attributes converge, then you can use the users to train memes, and then you have a feedback loop. I'll now like to pass it on to Saku, or Darius actually.
So currently we have our meme database in Excel as far as the attributes. We had one more final revision to our attributes after we clustered in R. Here's an example of our clustering in the bottom right corner. And eventually, once we finalize our complete database, we're going to put everything into Python. And we also have developed our recommender system, and this will also be placed into Python once the database is in. And then as far as creating the app, we're going to use Amazon Web Services for our backend, and hopefully we'll be able to use a Python interpreter to get that into Objective-C so we can have an iOS app as preferred to a web application. And that means we might need $99 for the iOS license, and we're also going to budget for the actual Amazon Web Service fee.
Thanks, Darius. Yeah, so basically the stakeholders for our project, it could be anyone. You might think that like a nursing home sounds funny, but you know, the world is moving forward in 30 years. That might be the primary activity. I feel like you've all seen like some elderly folks sitting at a casino for hours, things like that, and trying to find a good use for their time, and this could fit right in there. I think one of the more negative or stakeholders are more interested in negative sides could be workplaces, schools, when people are going to be quote unquote wasting their time using the application. And to be a little bit more serious, when we talk about younger and younger people have iPhones, smartphones, and we definitely need to figure out some sort of limitation factors, like what kind of memes can we show to people who are like less than 16 years old, what kind of, you know, the same way media content such as video games or movies have ratings. I feel like we should have similar ratings for memes too, because obviously some content is just not suitable for very young audiences. All right, moving on. Yeah, so for the testing portion, we are trying to finalize the clustering and the suggestion algorithm by the end of this semester. Hopefully we'll have a decently working version for demo day next week. And then next semester, looking at a smartphone app, most likely, or a web app, so we can get more user testing, send out a link to download the application or web link, so we can get more users to test the product and evaluate the performance. Yeah, I think Anisha already talked a lot about the implementation side. Basically, we just need the meme database, we move on to the clustering algorithm, and then using machine learning algorithm, we can finalize the app, and hopefully leading to time saved and enjoyment. As far as engineering standards go, we have the engineering standard concerning data privacy. So basically, we just need to be careful on how we collect the data so need to identify any of the people. Thanks for your time.
Cool. So hi, we are Team 6. We're working with a professor in the OID department. At a high level, we're working on designing an application that will improve the saving habits of the users. And Julia is going to go into more detail.
Okay, so just to go through our milestones, so these were the ones that we had from our last presentation in October, and I've boxed in red the things that we have decided to actually expand upon. So we still have these as milestones. We realized that it would be beneficial to get like more specific. So this is our current milestone timeline, and then as you can see, like in the green boxes are where we kind of have expanded upon the ones we previously had. So, and then we also decided to add one, which is our testing plan, which we realized we wanted to get a jump on this semester. And then we, all the check marks represent things that we have finished. And then because we kind of broke out some of our milestones, we decided to push some of them back, but we still are on track to finish everything that we wanted to do this semester by the end of the semester. And then these are our milestones and timeline plans for the spring semester. So we're really kind of just looking to finish up the app and also get ahead on testing. And we have a couple different test ideas that we're hoping to we'll talk about later.
All right, so this is just a little like basic flow diagram, but anyway, to get into like our project first, right? You can see there kind of like what the user wants to do when they're trying to use our app, right? So basically, we're looking for people that want to control their spending and also capture the savings from their mental account. And so basically, what makes us different from another like investment application or financial management application is that like most of them, you know, they're kind of like helping you with budgeting, or they're kind of doing some like automatic rounding up on different things you're spending. We want you to be able to take savings that you have from like your own mental accounting in your day-to-day, like maybe if you choose to take like an Uber pool versus Uber X, you're like, I want to save that money, or even like, you know, Black Friday just happened, you save on a deal, right? You think like, oh, I saved that money, but you didn't really save. We want to take those savings that you think about and make those like tangible and actionable savings that really go into your accounts and have an impact for you. So yeah, we have the user that wants to take control, and then they come join our app. So we have just kind of a basic lookup of what we want, like, you know, the users to do, and they come log in, email, password. Right now we're starting out with looking at using a Venmo, like getting users Venmo handles and trying to use that as a way to move the money. But that's kind of a placeholder for now. We're still like looking at factors to see if that will actually work out for our initial version. And then we have the user wants to create their savings goals within the app. And so that brings to like their kind of homepage where they can add goals that they want to meet. You know, this is where they can like actually put those savings towards something that they can get, whether that's retirement or something like on a quicker timeline, like a new car or a trip you want to go on. And then, so the time where the user goes into where they actually have to make an action is when they want to mentally account for some sort of savings in some transaction. And so they initiate the input process. So here we kind of have an example of that where we'll have like a menu. Like ideally we want to have a menu for different items where you can choose what you would have purchased, then choose in the next page what you actually purchased, and we'll calculate kind of the difference in savings. We also have another option that's kind of more manual where you just kind of put in dollar values. And then from there, you'll go on and choose, the user will choose like a goal they want to allocate that towards. So here's where they can kind of allocate that and like want to have something that kind of, helps you know what you're doing percentage-wise and gives you congratulations for that. And then your savings goals are completed after that.
In terms of technology, we're developing an iPhone application. We're using AWS for our backend. We've also put in a lot of work recently on designing our different tables and database schemas that we're going to use. Looking forward towards spring, we're going to keep iterating on testing feedback, refine our app, refine the front end. Right now, our first semester goal was more of a rough app to be able to start testing.
And real quick on the budgeting front, since it's a software application, we don't really have a ton of costs. Since we are using AWS, we have 2 student credits available to us. So we're using the first one now. We'll probably use the second one in the second semester. And if we do run over, we will use our budget for that. And we also have to pay for the Apple Store license. And now we have our quick demo.
It was just a flow. Really quickly, our testing plan. So we're currently working on right now getting prepared so that we can even test in the spring. So it actually requires a number of certifications and getting things approved. And then we want to do both a lab study and a field study in 2019.
Yeah, and then quick standards, we just want to be cognizant of how we're using people's data, privacy stuff, and then also dealing with financial data for users as well. Thank you.
Hello everyone, we are Team 18. So in terms of our timeline, we've split it up into kind of 2 components, software design and compression. Ben Finneran and Ben Yang have been both working on software design, and we put our October, November goals that we've met for the most part. And now we're moving on to December, and next semester, we're looking to really build a distributed architecture and handle multiple concurrent incoming calls to our database. We're also looking to build real-time response in that if an individual is going through a heart condition, then our entire application flow will give them or their primary care provider a response. On the compression end, we are looking to really sync up our device, the health device, with the internal database. And next semester, work more on predictive analytics in terms of identifying which types of heart rates correspond to which types of heart conditions.
So as a reminder of our problem, we're solving data stream problems for IoT health devices. So the current state of kind of what's available in the market, you can think of your Fitbits, your Apple Watches. These are devices that can track something like your heart rate and tell overall basically statistics about what you look like over time. Where research is right now is that they're able to batch up large amounts of data from these mobile devices over time and kind of figure out, based on these incoming, this incoming data, does this person smoke? Is this person stressed a lot? What's going on? But what the major gap here is that there's no infrastructure to allow these predictions and analysis to come back to benefit the user in real time. So that's where our project comes in, using these next generation devices to make a data stream pipeline to allow real-time analytics. And basically what we're talking about is we have multiple devices in our pipeline, and you can see they will hit an Amazon gateway where we will, one, store the data in eventually a distributed database. Right now, we're running into race conditions with having multiple devices. So that's something that we'll be thinking about going to the next semester.
And then eventually, we are running analytics that will eventually be given back to users for real-time feedback on their lifestyle.
Cool. And in terms of the technology that we plan on using for our project, the software that we're currently implemented includes a Dynamo database hosted on AWS. What we haven't actually included on the slide is also the MD2K application, which is hosted on our Android device that we have with us today. And in terms of hardware, we have the Samsung Neo J7 and also the Microsoft Band, which are pre-approved tools by MD2K, which is the organization we're working with. And the budget for these hardware devices come out to around $400, and we are also using student credit currently for AWS, and we will see how that fares into next semester as well. In terms of stakeholders, the people that we are really keeping in mind as we pursue our project here is the patients that would be wearing these devices and who are looking out for these conditions, as well as their caretakers who would like to be notified in a timely fashion if something were to arise. MD2K, which is a group that we are deriving a lot of from the code base that we are using, and as well as companies who are producing these devices that they may keep in mind the issues that we are also working on.
In terms of standards, our device is also a Class 1 medical device with exemption. And so the more important kind of standard that we're working with is HIPAA, especially since we're collecting a lot of medical data and private medical data, as well as running analytics on it. In an aggregated fashion, that means that we need to make steps to ensure that the privacy of the users is always protected. And so now we're going to do a quick demo, if Ada wants to help me. So as you can see, if you pull up the app and you press start, and I take the band and I wave it around, you can see that there is real-time data being streamed to this device. We've already showed kind of more the cloud side of it, and so right now we're working on kind of sending data from the Android device directly to Amazon. Okay, cool, thank you.
Hello, we are Team 15 for the naloxone device. I'm Darsh, this is Sid, Gurdon, and Kevin. Gurdon is a little sick today, so she won't be talking. And we're going to be discussing a wearable device that subdues the deadly effects of opioid overdose. So just to give you a reminder of our product, what is the problem, what is the solution? In 2017 alone, there were over 1,000 deaths due to opioid overdose. And the tragedy of that is that all of it was entirely preventable if addressed in advance. What happens is that opioid overdose leads to respiratory depression. You get shortness of breath, a severe lack of breath, and that leads to asphyxiation, which leads to death. What you can do to prevent this sort of thing is to have a device that measures your oxygen saturation levels, your pulse rate, your breathing rate, and determine if you need to be injected with Narcan, which can let paramedics to swoop in and save you before you die of asphyxiation. In particular, as we create this device, we have to keep in mind some type 1, type 2 errors. When should we inject the patient with Narcan? You would do it if they are actually undergoing that sort of depression. So we'll work to have an alarm that allows you to manually disable, as well as have a non-lethal dose of it. We'll work with rehab centers to bring this device into the community as well. Now I'll pass it off to Sid to talk about the design components of the project.
All right. So
one of the main reasons, or one of the main signs that someone is overdosing is their breathing rate drops sharply. With that in mind, the project sort of falls into 3 different stages. The first being getting a clean signal for someone's breath rate. The next being processing that signal to sort of decide whether or not you want to inject someone. And then the third stage being the actual injection. We've done most of our work this semester on getting a clean signal for the breath rate. This is not very easy to do on your wrist because your wrist doesn't breathe per se. But we've tried using a couple of different sensors, and that's, we've made most of our progress on that this semester. So as far as what we've achieved, our main goal for the overall semester was to develop a circuit and a sensor assembly that can let us get a clean breath rate signal. After that, we want to use next semester to build sort of the brains behind deciding whether to inject and then the actual injector. Problems that we've run into are that it's hard to build some sort of sensor like this. So we've been using finger pulse oximeters. We're trying to build a wrist-based PPG sensor, but for right now and like for the demo day, you'll probably see us using an accelerometer that's straight directly on someone's chest, measuring the actual chest cavity change as someone breathes.
So in terms of our budget, we used very low budget this semester, and most of it was the electrical components, so different microcontrollers, nanocontrollers, sensors, and so that's only $69. And for next semester, we are planning to invest the budget into the naloxone, the kit for the needles, and different components for the hardware that we have not invested in for this semester. Yeah, and so for our engineering standards, we are going to meet the engineering standards for injection, needle-based injection for medical devices, and we are also going to meet the IEE low power and for wearable devices, and the safety, cleanliness, and sterility of the needles that we're going to be injecting, which means that we are going to try to make the needles such that it's only usable once and that it's clean and sterile. Thank you very much.
Hi everyone, my name is Justin Shaw. I'm a member of team number 5. We're Modular Solar Panels. I'm a SIS major, Jin here is a ME major, Richard here is a Comp E major, and our 4th team member, Victor, he's not here today due to an interview, but he's also a Comp E major. So our problem was, how can we make static solar panels more efficient? Well, firstly, don't make it static because you won't be able to get as much efficiency from the sun's rays if we do that. And thirdly, how can we make it cheaper? Because current static solar panels or current moving solar panels are thousands of dollars and they are not very affordable to the average consumer. So the solution would be to create an affordable modular solar panel that would be easily repaired, would be easily portable, and that we could also have it move, have it be stable enough to get more efficiency and be good for a public use case. So now moving on to our fall milestones, we've hit pretty much every one, with the exception of creating an intermediate or final housing. The reason for this was because the parts did not come in time, and we hope to rectify this in the future, and hopefully this will be done by the fall demo. Now moving into the spring semester, we're planning on creating a better structure, better housing, and a better algorithm.
Right, so this slide kind of highlights our solar panel design. The text in black are what we are currently using, and the text in green are alternatives that we have considered or are currently considering. So the first component is the photoresistor. This gives us the light intensity at a specific location on the panel, and that information gets passed into our Arduino. Instead of Arduino, we have considered using, say, like a Raspberry Pi, but ultimately we think that it's just too power hungry for what we really need it for. We're trying to save energy here, not like use more than we need. And then within the Arduino, there's 3 different software algorithms that we're planning on implement. The first one's already implemented, and that's just a simple light sensing one. It determines in which direction there's more light and just moves the solar panel to that direction. The second algorithm is a scanner. It basically scans the sky and records the current values of each position in the sky, and then after it's done scanning, it'll just move the panel to that position. And then the final algorithm is a GPS-based one. It uses your GPS location to calculate where the sun is. And then that information gets passed into a servo. The way that our servo interfaces with our panel is through a 3D printed / laser cut housing. In the next semester, we're hoping to upgrade that into a carbon fiber rod just because it's lighter, and then to use machined aluminum to make it more stable.
Here's just a quick demo.
As you can see here, the panel follows wherever the smartphone camera, the smartphone light is going. And yeah, there.
So as you can see here, our budget is fairly cheap compared to the current products out there on the market, which can cost upwards to tens of thousands of dollars. Our stakeholder is the average person who doesn't know anything about solar panel and the way they should be oriented. So we want to provide a product that is cheap so they can install it in the homes or bring with them to wherever they like. Because we are targeting the average person, we want to make our product safe and reliable, and because of that, we were complying with several safety standards in context of battery safety and stuff like that. And moving forward, our testing methodology is that once we get our intermediate or final housing done and we can put the solar panels on, we will compare it to a static solar panel and we find the differences and improvements that needs to be done. And this will be our primary focus spring semester. Thank you.
Hi guys, we're team 2. I'm Brandon, this is Eileen, Peak, Fari, and we have the T-Bot. So just as a reminder of what we're doing, basically we're trying to build a robot that you show it a tea plant and it's able to pick and extract the tea leaves that we want. So I'm going to talk a little bit about the milestones that we sort of set out for this semester. So for this semester, we were trying to do a lot of sort of research and theory crafting before we started trying to build the robot and whatnot. So a lot of it was trying to go into how are we going to design the mechanical arm. So thinking about the kind of gripper that we're going to use, what exactly we're using to sort of pick and extract the plant without damaging it, as well as looking into what kind of software we're going to use in order to identify what kind of leaf we want. We still have a lot of work to do, especially from the computer vision aspect, but we've built a model of the mechanical arm, which is going to be good for us moving into demo week, so we can sort of show what we have. Next, Eileen.
Okay, so following the flowchart, we can kind of see what the system has to follow in order to
achieve the tasks. First, the computer vision component has to identify within an image where the actual leaves are located and determine if that leaf is a harvestable one based on the color and the size of the leaf. And then after locating where the target leaf is within the image plane, it has to be able to calculate where the leaf is located in the XYZ coordinate space. And then this coordinate is then passed into the mechanical side of the system. And then the mechanical arm will be able to move to that position, and the gripper will then harvest the leaf, and a vacuum system will harvest the leaf and store it somewhere else next to the robot. And something that some challenges we faced in the computer vision side is that in order to have like a proper deep learning model, we need a lot of labeled data sets, which is hard to gather. So we might start with a more vision-based system where it's using edge detection to determine those leaves instead of a deep learning approach. And then in terms of the mechanical design, we're exploring 3 different types of grippers in order to determine whether we want a twisting motion, a plucking motion, or a cutting motion in order to extract the leaves.
So most of our cost for technology comes in the hardware. Currently, we already bought the Intel RealSense sensor, which cost around $150. Right now, we managed to save costs on the robotic arm because we printed it from the 3D printer, but we're still looking into the grip, and we're still unsure of how much that's gonna cost. For software, everything's free. We're using PyTorch from Python for the image recognition, image segmentation. We're currently looking at adapting the YOLO model, which is used for image segmentation, into leaf segmentation. And our other costs are like buying plants and like keep on buying them for testing because they die out in like a month or something.
Okay, so starting with our stakeholders, our major stakeholders are like tea plantations owners and operators, and this can be scaled to other plantations. And our huge market is in China at the moment. So then moving to testing, we have started collecting a lot of data because we want to train our system on this data. It's going to be an iterative process. We want to make sure that we can identify the leaf to the precision of 2 to 3 centimeters. And then in terms of the hardware, we want to also make sure that our system is robust and steady for all the motions of this robot. So we are working on the joints, and during the spring semester, we'll be working on integration of these 2 segments, the hardware and the software, to make sure that there is clear communication between both. And then in terms of engineering standards, we are working on making sure that our system is very safe, and also it is ethical in terms of like the human interactions and how it affects and impacts our environment. Thank you.
Hey guys, we're Team 10, we're cars, so control the way robotics scheduler. I'm Bisher. This is Brianna, Connor, and Rohan. So generally speaking, the need is the fact that we need to enable scaling multi-robot systems, and usually the problem with that is that when you have a larger fleet, you would constrain the resources of your access point. So it's basically the controller. It connects all the robots to each other. So our solution would be a scheduling protocol, which takes into consideration the idea of co-design, where the communications resources would be allocated according to control input and to the current state of each robot. Basically meaning that each robot would get resources as it needs it. So the robot that needs most resources would get it. So this is going to be low latency, and as I've mentioned, it's going to be control aware. So Brianna's going to talk to you about our milestones.
Okay, so the milestones presented are the ones that we, these are how we successfully, these were our successful milestones. So in September, we worked on implementing just the communications protocol, which is the highest level, I guess, part of our project. It's what will allocate which resources goes to which drones. So we did that in September, and that's in Python. And then in October, we worked on the actual dynamics of the drones in simulation. So this was also in Python. And in addition, in October, this included the control for making sure that each of our drones would follow some specific path. So those were two discrete, pretty separate components. And then in November, our work has been to put them together in simulation in Rust, which is the robot operating system. We have had some setbacks. By the end of the semester, we at first wanted to do this in two actual F-110 cars, but the parts have not come in on time, despite us ordering them back in September. And the second thing is that Russ has an issue with, it was working pretty slowly on our computers, so it took us a while to find a sufficient environment to run these simulations. So we would have made more progress if not for those two setbacks. And moving forward, we're going to be working more to scale up the cars in simulation, so working with more than two, hopefully 5 to 10. And then in the spring, we'll do this on real cars instead of just in simulation.
So this diagram here shows the design that we're trying to implement. As we mentioned before, there's going to be one controller, which is that central computer rectangle, which is in communication with each of the robots or drones that we've been talking about, which are small robotic cars. They're basically like a souped up remote control car. As Berger mentioned in the beginning, the problem that we're working with is a communications constrained one, so that all of these arrows of communication cannot take place at every time step. So instead, the controller has to ask the cars at certain times for them to report back on their location, rather than that communication occurring every single instance.
Yeah, so most of the simulation is being done in Python, including the communications protocol and the vehicle dynamics. We're also working on integrating the Python code into ROS, which allows us to interact with the actual F-110 cars. As for the hardware, we've got 2 of the cars so far. We haven't actually begun working with them. So based on how things go, we may end up buying 2 or 3 more in the future. As far as stakeholders are concerned, the main ones really are Intel and the DoD, because this project is being done as a part of Professor Ribeiro's tie-up with Intel and the DoD. So, yeah. And lastly, for the standards, we've got a bunch of them. We'll be looking into them in the future. We aren't too concerned about them for now, because most of the work is in the simulation phase. But as we get into concrete implementations, we should adhere to these. Thank you.
Is this working? Yeah, I think it is. Okay, hi guys, we're Team Fly by Logic, which is Team 14. Wait, do I have to? So our milestones for that we did a couple weeks ago were making the old drone and flying a new drone, and we did those. We also developed a new interface design, and we are currently implementing it. So moving forward, we have divided our milestones into 2 categories. One is flying a drone, and then the other one is doing our mission planner, which we're going to explain more in the next slides. So in the future, we plan to continue having our drones fly more accurately so that they have waypoint following, and then also after that, integration. And then on the mission planner side, we plan to actually implement the user interface and then integrate.
So just to recap on the problem we're trying to solve.
Currently, there's a lack of existing user-friendly drone fleet mission controller, which incorporates time constraints in an urban setting. So our solution to that is using signal temporal logic, or STL, which incorporates time constraints. So two goals. First, to create a GUI, allowing users to find tasks for drone fleet, which will then translate it into STL logic for the trajectory planner. And this trajectory planner will then spit out kind of trajectories for each drone. And then we also need to improve the existing drone sensors, as well as like the low-level controllers, so to achieve more complicated maneuvers. Here's like a block diagram for what we're trying to achieve. So in top, you can see there's the UI that translates user inputs into STL, and that gets fed into the trajectory optimization algorithm. And that gives each drone its unique trajectory, which achieves minimum separation and other things. So here's like a mock-up of our UI. It's still getting worked on right now, but we've kind of finished like a rough skeleton of this. Yeah.
Okay, going to the technology and budget. So this semester we have 2 working drones. We have, so for the hardware we bought a drone kit, a DJI 450. We installed props, ESCs, and a Pixark or droids to make it fly. And for the software, as of now, we're using a Q ground control. And we have a short demo video. Well, I guess not. For the spring semester, yes, say yes. Yeah, you can see the nice drone taking off. Yeah, that's what we have now. And as time goes by, you're going to see more fun stuff happening. And for the spring, we plan to introduce 3, maybe 2 more drones. And we're basically going to have a whole fleet. And yeah, thank you. Oh, we have one more slide, and Yash will take care of that.
All right. Next slide. So yeah, our spring semester is going to be mainly our implementation and testing phase. So right now, we've been pretty much like alternating between weeks as far as like working on the drone and then working on the UI. And in the spring, we're going to put both together, and that's where we're going to have to do a lot more testing to make sure that our UI is communicating with the algorithm, and the algorithm is giving the trajectories that we want, and the drone is actually performing them. As far as standards, we talked about this last time. Many of them are in flux, so we just have to stay on top of them as far as like FAA regulations. And then we're still waiting to see if the UK will release drone standards as far as how drones should operate. Thanks.
Okay, hey everyone, for those of you who don't know me, my name is Andre, here with Jeet, Lucia, and Marcos couldn't be here today, but we're gonna present an update on SolarRide. So just a recap, the problem that we're trying to solve is the long commuting times for for students that leave off campus, and the general lack of transportation solutions to campus for students. And our solution is SolarRide, and as a reminder, SolarRide is a network of electric scooters, much like the Lime and Bird scooters that are already in several cities for the Penn campus, basically ran by Penn. So in terms of an update, in terms of the milestones that we proposed, So we had said that we were going to develop a network model beta, and Lucia has worked a lot on that, and she's going to present on that later. Then Marcos and I have also worked a lot in the mobile application, and we have a good beta running, which Jeet is going to talk about. And also another thing that we've been doing is trying to meet with some of the stakeholders, which include Penn Transit, the city of Philadelphia at large, the transportation department, and the university in a more broader sense. And one meeting that we had was particularly useful because we learned where the city stands in terms of allowing electric bikes to come in. And although the general consensus was that the city is not yet able to allow Bird and Lime and electric scooters to be roaming around, one of the main reasons for that is because of the dockless aspect of those companies. They don't want scooters lying around, and we feel that we have leg up because we are going to have stations where the scooters are going to be docked. But there's still a lot of lobbying going on, so we might have an update, a better update next semester as this is under development. And in terms of the implementation plan, we have advanced a lot in it. We have figured out how we're going to do the geofencing, which means that if a student wants to take or if someone wants to take the scooter outside of a radius, we're going to lock the scooter. And we're currently working on the design plan, which we're going to present. And then next semester, we're going to work a lot on the actual implementation, so actually building the stations and actually developing the traffic model and completing the app. So now Jeet is going to talk about what we have done.
So far we've connected the Arduino with the scooter, and we've used the GPS receiver, and we have started getting data, although we haven't tested it properly outdoors because the system is still tethered. We've also connected it to Wi-Fi and have gotten data streaming to our Firebase database. So this shows the whole system connected with the bike. This is the app that Marcos developed, and you can see in the top left, that's the real-time database on Firebase. And after that, the Firestore is what connects to the app and sends real-time data about the GPS. And then you see the red dots, that's what the scooter is, and that would, in real time, that would move around.
Okay, so another part of our project is being able to kind of see the demand and where it's going to be best for us to have the stations and also how many bikes we'll need. So this semester we are trying to do a beta test to see how exactly we can represent this data and get the information. So this is data that we use in general senses of Philadelphia. The heat maps are where people mostly live around campus, and then the other points show popular places of where bike sightings and bike paths and things like that. So our next step is we've also been collecting data of our own of specifically where Penn students live, not just people in Philadelphia. And then we're also going to be doing where we're collecting data to see where exactly to go to in class, for example, what stops are most popular with Penn Transit and where we really think it'd be best for us to have our stations, and then continuing on to develop a model and emphasizing more of that data into this map. Some of the other standards that we're following, though, is like Andre mentioned, a lot with City of Philadelphia and Penn Transit and UPenn to kind of see where exactly they can travel, whether on the sidewalk or the bike lane is better, or at what hours they can go through Locust Walk, and also keeping these in mind when we continue to develop the data.
Yeah, and so far with the testing, we haven't done any outdoors untethered testing yet, but we've done a lot of testing in the lab, and we've started getting good data out. We still, in terms of implementation, we've done quite a bit, but we still need to implement the locking system for our brake. So what happens when someone finishes riding it? And in terms of the standards, I guess we just have to follow the IEEE standards, and that's about it, because we don't collect any user data.
Hello everyone, we are Team 12 and our project is SPOT, which is an intelligent parking spot identification system. Basically, the way it works is with a system of cameras, along with our computer vision algorithm, the end user is able to see the available parking spaces, select their desired spot, and be navigated to it. So taking a look at our milestones, early on in the semester, our first goal was to take test images. Our next goals revolved around getting our camera working, along with its ability to upload images. That was originally slightly delayed due to waiting for parts. We've also run into recent bumps, so we're hoping to have that done soon. Our other goals for this semester, such as detecting lines and being able to detect open spaces, were both completed. And finally, based on feedback from our TAs, we've decided to add an additional milestone for this semester. We're hoping to have a basic demo of our app ready for demo day. And looking forward to the spring semester, our very first goal is to kind of integrate the whole system together. Going forward, we're then really going to split the team, so half the team will be focused on further developing the app, while the other half of the team will focus on the computer vision algorithm. From then on, we'll hopefully demonstrate successful operation of the entire system, finish our business plan and analysis, and have a fully functional product for demo day.
So just a quick reminder of what our design was. We made a few minor tinkers to it. Initially, what we envision is that an individual would go up and pull out their smartphone, as there may be a couple of miles away from from where they plan on going. They'll click enter the location, and then the system will tell them exactly where there are. The system will first go to the camera and take an image of all the available parking spaces in the area. From there, it'll run it through an algorithm and determine which parking spaces are actually open, and it will give it to the user on their application. The user will then be able to select the parking space they wish to access, and from there, they'll be routed over to that specific location, and they'll be able to pay directly on the application. In terms of the one change we kind of implemented was, instead of continually taking images, we would like to just have the system take images whenever the user selects, and basically have it set where there'll be a user can go through and select the area and how far they're willing to go from the individual spot to where they're parking.
So in terms of the technology we used, there's really three components. There's one hardware element, which is a Raspberry Pi with the camera, which we're using for the camera system. We have Python and OpenCV for the computer vision algorithm, and we have Java for Android app development. You can see our budget right there. $30 for camera, $85 for Raspberry Pi and starter kit for a grand total of $115. And then on the bottom right, you can see an array of 8 images. That's just sort of a walkthrough of the steps that our computer vision algorithm takes, starting from the top left, and the end result in the bottom right, where you see detection of open and occupied spaces.
Cool. So the main stakeholder we identified is the city of Philadelphia. And this has led to talks with Andrew Stober, who is the VP of Planning in the University City District, as well as the Philadelphia Parking Authority. The main challenge with this is keeping these people engaged due to long response times for these public officials. There's also some ethical considerations that we wanted to talk about for using the city as a stakeholder. Privacy in terms of the app that we plan to build and data that we plan to store. Also, we want to ensure that our cameras aren't spying on people and they're only watching the roadside. And then finally, we also plan to have this surge pricing algorithm. So since parking is normally a public service, we want to consider how that works out. And then finally, in terms of testing, we plan to put a Raspberry Pi camera looking over a single street. We want to build out our app to handle this and expand when able. And then some engineering standards that we've identified are related to storing and archiving public transportation data, which is relevant when we expand our app. So thank you guys.
All right. So our project is InVisi, and we're building a smart invisible aligner case that will help deal with patient compliance problems. Unfortunately, today patients tend to overestimate the time that they're wearing the aligners and then proceed to come to providers and complain about the inefficiency of the treatment. Well, that won't be the case anymore because our product will allow the providers to track the usage of the aligners. Moreover, when you're prescribed a treatment, you're given about 10 to 15 different aligners to be used at certain times. So our detection system will detect whether the aligner that's placed in the box at a certain time is the one that needs to be used by the treatment.
So in designing our system, we have to deal with two stakeholders, patients and providers. We have to deal with a couple of engineering standards, and we have to also make sure our system is effective by testing it. So first with the testing, the dental school has agreed to provide us with 5 test subjects. With the 5 test subjects, we're going to execute roughly a month and a half of testing in which we're going to give the cases to the test subjects and have them actually use the cases and see if we're able to effectively measure when they're wearing the aligners, when they're not, and if our push notifications and our other sort of technical apparatuses for reminding them to where their aligners are actually effective. In terms of engineering standards, there are 2 that we're focused on. There's HIPAA compliance and there's Bluetooth Low Energy IEEE compliance. HIPAA compliance is going to be pretty easy since we're not really storing that much private information about our patients. In fact, as of right now, we're not storing any of it. And Bluetooth IEEE compliance will also be really easy as long as we don't barrage noise into the Bluetooth atmosphere, which we don't intend to do.
So in terms of the software side, we built a web application using Gatsby and React, and then we stored the data using Google's Firebase.
From the hardware perspective, we customly created a SolidWorks model, and we're using an Adafruit Feather microcontroller that allows for BLE capabilities and also usage of our battery. And we're also using a barcode scanner to detect the different aligners and a pressure sensor to track the usage. For the budget breakdown, we're really not using that much money. Fortunately, we have the $250 premium we got from the Rubber Catalyzer, and the Adafruit Feather is about $30 worth, and the rest of it is 3D printing costs and software.
So in terms of milestones, we've come a long way since the semester began, like, 5 or 6 years ago. We've completed our development of a very basic, rudimentary, but effective software platform that relays information from the device through a mobile app to our server, in this case Firebase. And we've also built a web app that will then go ahead and display that information in real time. So we have the full software stack at a very basic level sort of built out. So our final milestone for the end of the semester is going to be sort of building out the data visualization / UI side of that and allowing our users to not just receive the data in the abstract, but also actually view that data, which is pretty important usually.
From the design perspective, we have the SolidWorks model. Inside the SolidWorks, we are carefully mounting the pressure sensor to make sure we get the most accurate reading. And we also have a barcode scanner that's currently manually triggered, but we're working on connecting a small inverter there to make sure that we can electronically trigger the barcode scanner to make sure we can save energy. And then the data is transmitted to a web application through BLE, and Daniel can talk about that.
The BLE from the device communicates with the Bluetooth transceiver on the iPhone, or the mobile device. The mobile device then sends the information to Firebase, and then Firebase handles the real-time querying, data querying to the web app.
We have a small demo. It's not fully functioning to what we want to see, but it does have a generic demo. So here's the application, and you can see the aligner with a pressure sensor on it. No aligner inside. No aligner in the case sign, and once we place the aligner, we see that the sign changes to aligner in the case. And Sarah will talk about the plans for a spring.
So for the spring semester, we plan on adding additional functionality. So we hope to add a social aspect to this project. We've noticed that other companies have showed real results when they implemented that, and that improves patient compliance with the device. A second thing that we would like to add that adds compliance from the user side is GPS information. So the ability to remind a user, hey, your case is 5 meters away, you might be about to lose it, and give them that notification and that help, as well as provide an additional dimension and metric when we're trying to understand that patient's behavior. On the healthcare side, we hope to expand into looking at dental caries and excessive dry mouth. These are two diseases that have indicators that can be tested and were brought to our attention by people within the dental school as well as our advisors, and so we hope to expand into that space. And with that, thank you.